how the Big Bang works. We think, well, we're pretty sure, and I'll show you why, that as you go back in time, you go from the present day, 13.7 billion years, you go backward. And the question is, what is the thermal history of the universe? What temperature is the universe? And I'll show you why we know what the temperature is. The temperature increases as you go back to the beginning of time. That means that the energy per particle increases sharply. And finally, you get to a time at the very beginning of time, and we got to understand what that is. What does it mean to talk about the very beginning of time? How can we make any sense out of that? Now, these are hard questions, and they have attracted the audience, I mean the philosopher, not the philosopher, they've attracted theoretical physicists from all over the world to study this. The reason is that the high energy aspects of what happens unifies physical law in a way that we can't see on observations today. So we go backward. The time we're going to talk about expressly is something 380,000 years ago, and I'll tell you why we talk on that. Then we go back to a tiny fraction of a second. I'm going to tell you today the evidence of the universe as the universe existed for 3 minutes. How can I say anything about the universe when it's 3 minutes old? But I'll show you something that is pretty damn good. It's really convincing. This is what convinced every scientist that this is right. This theory is sensible. So I'm not talking about science fiction. This is real science with observations, theories, and everything. Okay, now the thought of the universe is that at present we live in a universe of galaxies, and we can go backward in time. Go backward in time to a time where galaxies form, to a time known as the recombination era, to a time of particles, electroweak interaction, electroweak unification of the weak force and the electromagnetic force. Remember, there are 4 forces in the universe. Gravity, the first to be studied, electromagnetism, which was made beautiful by Maxwell in the 19th century, and then 2 forces, the strong force, which holds together the nuclei in an atom, and the weak force, which is responsible for the decay of atoms. And the weak force always has neutrinos involved. The forces were united at this time. What time is that? That is, what does it say? This is a ridiculous time. What is that? 10 to the minus about 30th seconds. It's really a ridiculously hot time. It's very early. Before that, up to 300 seconds, 5 minutes, the protons and neutrons were all that were in the universe, and the electrons. And they did something pretty strange, and I'll tell you that in a minute. Before this, there was something called, well, it might have the order wrong, the inflation epoch. Then there was the gut epoch. The gut means grand unified theory. And that was the time when the 3 forces were united. And those forces are the strong force, the electromagnetic force, and the weak force. They're all the same theory. This is every bit as powerful as electromagnetism, which was unified by Maxwell in the 19th century. If we can unify the forces, they want to do it. And now they've got these 3 quantum forces that get unified. And where's gravity? How does gravity unify with this? And solving this problem has attracted the particle physics audience like nothing else. There have been more papers written on the first 10 to the minus 35th seconds than you can believe. 10 to the minus 35th seconds, that is no time at all. And yet there are papers and papers and papers written about this. It's pretty impressive. That is an epoch when the universe was made up of probably 10 dimensions. Now, has anybody heard of this so-called universe, 10-dimensional universe? Okay, one. There is a show on television right now. I should have told you about this. I'm stupid not to. On PBS, Novae, a series of Brian Greene. You can probably see the old ones. It's a 4-part series, and he's talking about theory of everything and why scientists are attracted to this theory of everything. Okay, we'll talk about how it impacts this theory of everything. I'm not going to talk about it in detail, but we'll talk about what it says about our universe, and it is pretty impressive. Okay, so we have a lot to cover. Cover this first 10 to the minus 300 seconds I have to talk about. That takes a long time to talk about. So the universe is very, very strange. All right, so let's go back and remind ourselves what I said last time. If this is our universe today, right now, in the past, the universe was a smaller balloon. Remember, this is not the real universe. This is only a 2-dimensional universe. It's on the surface of a balloon. You specify the coordinates by giving it latitude and longitude, for example, like on the Earth. And that's the full specification of the coordinates. You don't need anything else. 2 coordinates. And to make it, and you embed a balloon into a 3-dimensional universe in order to make it real, in order to draw it and understand it. Similarly, our 3-dimensional universe is drawn in a 4-dimensional universe, which you can't visualize. It's hard to visualize it. But the 4-dimensional universe gives the ability to draw a sphere in that universe. Now, this particular universe has a finite size. You go around and around and around, and you can come back and see yourself. You can see the back of your head if you look really hard. All right, that might be our case. We might live in such a universe, but we don't know that. All right, we might live in an infinite universe, and we're not sure. All right, so as you go back in the past, all the wavelengths are stretched. This is a shorter wavelength than here. That means that there's going to be a redshift. The photons are going to be stretched. If A is the size of the balloon, they are stretched. Z naught is known as the redshift. H naught is the Hubble constant today. The redshift is simply 1 plus Z is the ratio of redshift. Oh, here, let's take this one. 1 plus Z1 is the ratio of the size today divided by the size at the time you're questioning. So this will be, say, A, the diameter of the balloon. And that's the redshift. Now, this is far better this is the right definition of redshift. And a particle sitting on this balloon is expanded. He does not sense any velocities. He's not moving fast. It's not a Doppler shift like when you analyze the local galaxies flowing away from us. You think that's a Doppler shift, but it's not. It's just the expansion of space. All right? So the expansion of space is very, very strange. Now, when you look at faint galaxies, you're looking in the past because the light travel time is so long that those galaxies took forever. They took 10 billion years to get here, for example, 12 billion years. And you can identify the galaxies by their redshift. You measure the redshifts and find that they're at redshift 3, for example. Most of these objects are redshifts 2 or 3. Now, how do you see that? That means that you look at a spectral line, say a line that's 100 nanometers, and a line comes out at 200, 300, 400 nanometers. It's 4 times bigger. And remember, 1 plus z is the size of that universe. So instead of seeing it at 100 nanometers, it's detected on your laboratory, in your spectrograph on the telescope at 400 nanometers. Every line is shifted by that factor. And that tells you the object was emitted, the light was emitted from an object when the universe was 4 times smaller than it is today. The universe was 4 times smaller. Now remember, this is the way to interpret it. Don't interpret it. Do not interpret the redshift as you could have interpreted the redshift as the velocity of recession equals h naught times d equals and it equals z times velocity of recession is equal to, it goes, I'm sorry, it's proportional to z. Z times z times v over c. I'm sorry. Right, that's what it is. Okay? This gives the lambda. This is the lambda observed over lambda emitted. This is a slow motion, and if you put in z of 4, it appears as though the velocity is too high, as though the redshift is, the guy's moving away from us at 4 times the velocity of light. Well, that is not right. It is not moving away from us at all. No galaxies are really moving from us. They are simply tied to this space-time, which is expanding. It is not the motion of an individual galaxy. It is simply the balloon that's expanding. All right, so if you look at the galaxies in a little detail, you can see interesting pictures. For example, at redshift 1, if you look at it, these are galaxies. These are all galaxies. At redshift 2, here they're sort of blobby. Redshift 1, they're blobby, a little bit neater. Now remember the movies I showed you Tuesday about all the galaxies forming, about them crashing and being a mess as they collide and form. Well, these look like they're colliding pieces, just like the movies showed. They look like galaxies in formation. But this is 10 billion years ago. They're very different. So it's appropriate. The galaxies 10 billion years ago didn't look like galaxies today. All right. Now, the cosmological principle. Here is the basic thing about it. The cosmological principle is the universe is homogeneous and isotropic. And what that means is that clustering of the universe is supposed to be it's not real important. But the clustering of the universe is real important. And the universe is inhomogeneous on scales of 100 megaparsecs. But on bigger scales, it's quite smooth. Okay, on larger scales, the universe appears homogeneous. That means the same in all directions, and isotropic, which means the same in all, same in all locations for homogeneous. Isotropic is the same in all directions. The universe appears to be homogeneous and isotropic. Okay, the cosmological principle states that any instant of time, a typical galaxy sees the universe, and it doesn't matter which galaxy you pick. Pick another galaxy far away, and it will see the same universe as us. That is the consequence of the cosmological. Yes, you have questions? Question? No. Okay. Okay, that is how the cosmological principle works. Now, all observers see isotropic Hubble expansion, that is, it's smoothly expanding away from them. They appear to be at the center, and they appear to have condensed at a time which is approximately 1 over h naught. That is the time that the universe appears to have been born, 1 over h naught ago. Okay, as the universe expands, the density has to go down. There's no question about that, because we've conserved number of particles, conserved number of galaxies. In the past, density had to be very, very high. So that's clear. Okay. Now, we showed this movie, and this is what the universe looks like on large scale. A gigaparsec, that's 1,000 megaparsecs, 500 megaparsecs, 250. These voids are in all the universe, 125, and we'll say where they come from. And as you zoom in on a galaxy cluster this time, the universe becomes more and more inhomogeneous. We would be a galaxy off on the side, maybe one of the bright dots, but we're not in a cluster center. So this is the center of a cluster. And then it goes out. We are approximately here relative to clusters. We're not in a rich region. It's not that conspicuous. In fact, there's nothing you could do to say, we live somewhere out here. But lots and lots of galaxies are out there. Lots and lots and lots and lots of them. The number of galaxies is bigger than the number of stars in our galaxy. It's easily bigger than 10 to the 12th. We can see that many. That's a huge number of galaxies, just in our region. All right, now, these are in co-moving coordinates, if you recall. Co-moving coordinates meant that co-moving coordinates means that you imagine a balloon of that early size, and you draw a grid pattern on it. All right? And you draw the same grid pattern. And you say, here's a galaxy, and here's another. Here's a galaxy, here's another. These are the same galaxy as the universe expands. And yet, the center, this guy sees this guy receding from him. That is the expansion of space. All right, now, these movies are done in co-moving coordinates. And that means that as the movie progresses, it just shows the grid. It's not showing the expansion. So let me show you the next one. Now the question is, how the hell did the distribution of galaxies get to be so irregular? How did it get to be so irregular? And I said last time it was because, well, you can imagine the universe is smooth, but then the irregularities represent density enhancements. They're higher density than the other material around them, and they'll attract the material to them. Now, I'll show you this working on a slide. All right, this is the universe at some time, and you see the white stuff, that's the density regions. This is the holes, and the white stuff's getting bigger and bigger and bigger as it attracts the matter. So you can move, it's moving in, growing over time, moving in, and leaving underdense regions behind it. This shows how the matter grew with time. It started from initial fluctuations, which are pretty small. And over time, they grew up just through gravity acting on them. And this is in co-moving coordinates, so you can see what's going on. All right, that is the growth of structure on large scales. And this is how it works. Now, remember that if you suppose we measure the distance between 2 points. These are galaxies, say, A, B, C, D. And you say, well, one galaxy is here is us as the universe expands this way, and this is the distance from it. So you say, well, let's take this galaxy. Here's us, and here we'll take galaxy C. We'll say this is galaxy C. And in the interval, it expanded up to here. And the distance between them, this is distance, the distance between them has grown. And that's how the universe expanded and everything receded. All right, so in this coordinate system, the fixed latitude and longitude, you can get a sense of what I'm talking about for co-moving coordinates. All right, everything, you characterize the entire balloon by specification of a function which can be called R of t, the size of the universe, or sometimes it's called A of t, the size of the universe, doesn't really matter. And you sit on a fixed grid point. The real important issue to remember is that everybody sits on grid points and doesn't move. Now, what makes the galaxies move is the attraction of a nearby cluster that pulls the galaxy off of the grid point to make the cluster bigger, as the previous movie showed. Okay, then describing R of t is everything. Okay, now Einstein in theory of relativity, when he put out the theory in 1915, thought like everybody else that R of t should be a constant. That means the universe is static. That's what Newton thought. The universe is static, meaning it's not expanding or contracting. And he thought, well, that's how it works. And what he saw, as he worked through the mathematics of the theory, he discovered that R of t is not a constant in his theory as he originally wrote it. It cannot be constant because the universe in his original theory is either expanding or contracting. And that was inevitable. So he modified his equations. He added a term. He could not conceive the universe was expanding. Even Einstein was unable to conceive this observation. This was quite quite shocking to discover the universe is expanding. Now it's so routine, you've learned about this since you were children, and there's nothing to it. But it was not simple. To realize this was amazingly unbelievable. But the evidence was unambiguous that the universe is expanding. And he modified his equation by adding something called a fudge factor. Fudge factor is just a term to fudge the results. So he fudged the results by adding a term known as lambda. Okay, I'll say what it is. This term makes it possible for r of t to be constant. So he added this term to his equations, and suddenly he was able to find a universe that was constant. Now, this was really a bad idea. After the discovery of Hubble in 1929, the theory rejects the lambda term. He labeled it the biggest mistake of his life. He's quoted as that. Because if he had left the theory alone, not added that stupid term lambda, the expanding universe would have been the fourth major prediction of general relativity. As it was, there were three predictions that turned out to be right. One is the bending of light from a nearby object. Two is the redshift of light coming off stars. And three is, three was the perihelion shift of Mercury. So three points where he'd already met the theory, had met the observations. But this would have been a fourth point. And he didn't, he missed it because he goofed up. But, all right, so he rejected it. Nowadays, we do use it. All right, so what do we do? All right, so it is possible to solve for r of t in a simple way. I'm not going to expect you to know this. You can do it by talking about the mass within a sphere of a certain radius. That mass is 4 pi over 3 r rho naught times rho cubed. You then, all you do is talk about energy conservation, and you say the energy is the kinetic minus the potential, and you say energy is conserved, and lo and behold, you get that this is the same as Newtonian gravity. Bound universe is if the energy is less than 0, unbound if it's greater than 0, and you can see you can solve for rho naught. If you want the density to be conserved, you want us to live in a critical universe, then the density has to be specified at approximately at this value, and this works out to 10 to the minus 30th grams per cubic centimeter, or 3 hydrogen atoms per cubic meter. And that is a ridiculous vacuum. It is an incredible tight vacuum. Much better than a vacuum you can make. Okay. So the expansion slows down. The age of the universe is slightly less than h naught, 1 over h naught. And the age of the universe turns out to be 9 billion years divided by the ratio of h naught over 70. All right, so 9 billion years is the estimate of the age of the universe. But if you find galaxy clusters, if you find suppose you go and look at galaxies and discover a cluster that is 12 billion years old, and you say the entire universe is only 9 billion years. Well, that's a conflict, right? You can't have a galaxy cluster be that old. You can't have it. It doesn't fit the data. It doesn't fit the theory. And so scientists knew this. We knew that the universe, this was too young an age, and it wasn't acceptable. And so we had hints. In an early day, 20 years ago, we had hints the universe was not describable by critical density. It did not fit a critical density. All right, so remember the curvature of the universe that we talked about. The universe is flat, meaning that Euclidean geometry works. It's curved if Euclidean geometry does not work. This universe is infinite, the flat universe. It'll expand forever. You could have positive curvature like this, and the lines intersect. The angles of a triangle are greater than 180 degrees. Okay, these are all true. This universe has no edge because everything goes around here and no edge is seen. Eventually this universe recollapses. Now, alternatively, the universe could be this shape, which is sort of the surface of a saddle. And in that case, the circumference is bigger. This has no edge. This universe escapes its own gravity and keeps expanding forever. All right. Now, this is very different from the case of a black hole. Remember, the black hole was a point in space. The point in space was really heavy, and it attracted matter, and it bent the sheet, all that stuff. That was the solution of Einstein's theory of relativity. On the other hand, this is uniform. The curvature of a uniform space is no dimples that make the universe rippled up. It's just the whole universe is curved. So it's a somewhat different solution. But that's okay. The theory still applies. All right, and remember I told you this, that if we plot the distance between galaxies as a function of redshift, this is a present, and we go back in time, this is what a recollapsing universe would look like. And clearly, this universe does not fit the data from supernovae. Neither does this universe. This is a critical universe that has just enough mass to make the universe expand and then stop. It doesn't fit the data. This universe, at which the universe has an open sense, like the saddle surface, doesn't fit the data either. It just doesn't fit the data. Those were the three cases I talked about. None of them fit the data. This was a complete surprise to the entire community when this was realized. And the data from the supernovae was very, very clear. There was no getting around this. And the conclusion is the universe is none of those possibilities. Instead of being a negative curvature, like here, the universe has a positive curvature. First it had a negative curvature, then it accelerated. And that means that the universe is controlled by something else. You would never see a positive curvature if the universe were controlled by matter. You put any matter in there, and the universe cannot do that. So it's something else that makes it do that, not dark matter. It doesn't do that. This has to be something incredibly strange. Okay, now, cosmological redshift. Again, it's incorrect to talk about Doppler shifts. That is not what's going on. Doppler shifts do not make the redshifts. The wavelengths are stretched because of the expansion of space, and that's the redshift. That's all it is. That we observe the redshift. Okay, and they observed they're expanding as space is expanded between the observed redshift and the emitted redshift. And the ratio of the two sizes gives you the redshift. That is what you see when you measure redshift of galaxies. When the projects that I just completed, we measured redshift for 50,000 galaxies. And they were all, most of them were in the range of 1 to 2. That meant the universe was actually, no, I'm sorry. The observed wavelength was twice what the wavelength was when it was emitted. We saw lines of oxygen that should have been, they would have been detected at 372 nanometers, and instead we saw them at 800 nanometers, for example, 900 nanometers, 1,000 nanometers, 700. We saw them all at tremendous distance. Very routine, this type of work. And we conclude that the universe was smaller when those photons were emitted. Okay, when you observe quasars, you observe the universe by these ratios. Okay. Now, what is the universe expanding into? That is a fundamental question. We've had a sphere that's expanding. Okay? Suppose I say three-dimensional space is everything. Suppose it's infinite. What does it expand to? It just expands. Don't worry about it. It doesn't expand into anything. It is everything. The coordinate system are simply carried out there. They expand out there. There's nothing outside the universe. Don't worry about it. You cannot see outside the universe. We will never see outside the universe. So the universe is incredibly strange. Now here I will draw a picture. All right, the universe is very large. So let me draw a grid. And we'll suppose we put us here. And we look out in the universe. And you look and look and look. And we know that the further away you look, the higher the redshift. So, for example, I'll draw a circle. Of course, this is a circle in 2 dimensions. It should be a circle in 3, right? Now, what is this? This is distance. Now, I'm in a co-moving coordinate system. Everything is on the co-moving grid. I'm not dealing with the expansion. So you say, well, what is this distance? Well, for example, you could put this at redshift 1. That is, the time it took the universe, the photons to travel from here to here, was such that it had a redshift of 1, and that meant that the universe was half the size when it saw it. Redshift of half is not as far. 1/2. Redshift of 2 okay. Redshift of 3, it turns out that they're not really spaced evenly. 3, 4, now what does that mean? That means that when I look back from here, it took the universe a long time to send that photon to me. All right, what do you say if the universe is 13.7 billion years? That is to say, I'm going to look at a photon. You can't do this, but I'll say you look at something that has been moving freely to us since the universe began. All right, and I'm going to draw it right out here. This turns out to be z equals infinity. You're looking, the light travel time is 13.7 billion years. That means you cannot see further. There's nothing you can do. There is no way to see further. Let's draw this grid further. These points they have a light travel time that's older than the universe, so we haven't seen them. There's no way to get there. So same with these. We don't know about these galaxies. They're too far away. Now, this whole region we can see is called our horizon. For obvious reasons. That's as far as you can see. It's actually a cosmological horizon. This is as far as you can see, no further. All right, and in terms of this balloon, you draw a balloon, and it might be just this. You're seeing, this is the horizon here. There is a lot of universe out here that we don't know about. Now, the question is the universe homogeneous? Meaning it's the same everywhere? Or not? We can't see this. We assume it's homogeneous, but that's just a guess. We don't know what it is. The observations, there's no observation we can ever do that'll say. Okay? All right, so so the universe is not expanding into anything. It's everything. All right? And there's nothing, don't worry about what the universe is expanding into. If your mother asks, well, you learned about cosmology, I've had a question, I don't understand what it's expanding into, tell her not to worry. There are more serious things to worry about. Okay, as we'll see. Okay. All right, now the thing is here, why is the Big Bang not an explosion? It is not an explosion at all, because this sphere goes all on forever. An explosion has a center where the sphere goes on, and then it's outside the sphere, and it's not the same. The Big Bang is not an explosion. What happened is, long ago, the kernel just expanded really fast. Why did it expand? Why did it take off? Can we ever answer that question? That is a fundamental question. Okay, now, here we can say, to see this point, this guy is receding from us at the speed of light. And out here, these points are receding from us. This point is actually moving faster than light speed. Is that a problem? Here I've been telling you can't move faster than light speed, and yet the universe does. How can I get away with that? Anybody? The universe is expanding faster than light speed. From here to here, expands faster than light speed. If you try to measure it, you can't, because it's expanding too fast. Because you know that the photons only travel at light speed, and you can't catch up with them. What has happened is that the expansion rate of the universe is not governed by what we learned in special relativity. It can do it. It will expand as fast as it needs to. All right? There's no speed limit on the expansion of the universe. The universe is not a particle. It's not a photon. It is just space. And it blows up. Now, certainly that's something you can't do with an explosion, to get the explosion to travel faster than light speed. So don't think of the Big Bang as an explosion. That's completely wrong. All right? The expansion is the growth of the grid pattern. All right? And the balloon expands fast. And that expanding grid pattern is what you see. All right, so now imagine you're on the balloon. It is, if it's a finite area, the expansion of an ant, he's walking on this surface, and he sees the universe expand around him. He does not sense the universe is expanding fast. In fact, the other part of the universe is far away from him. He doesn't sense it at all. Okay, evolution. This is governed by Einstein's theory of relativity. The fabric of space-time is manufactured. It makes it up. It just makes it. Okay, and that is really necessary. That is actually what happens. Space is manufactured. Now, the question is, how can we measure this? How in the world do you think astronomers and physicists actually have anything to measure? It seems more like a philosophical argument, but there really is data you can bring to bear. It's amazing that you can do something, that you really can do it. How do we measure the curvature of the universe? Well, one way to do that is to measure the density, compare it with a critical value. And we define a term called omega, which is the density we measure divided by the critical density, which we can compute. We say omega is closed if it's greater than 1. It's open if we see a value less than 1. So that's a parameter we can compute, and it is computed. We measure the expansion rate. We see how fast it's accelerating. That's hard to do, but you can try to do it. But you can look at geometry of space. The sum of the angles in a triangle. The 180 degrees if it's flat, greater or less than 180 if it is curved one way or the other. But the space is so close to flat, it's very hard to do that. So those classical tests of curvature are not really practical. People tried to do them throughout the 50s and 60s, and it didn't lead to any great conclusions. Okay, now you can study how strong the gravity must be to stop the entire universe from collapsing. And that is the critical density. Okay, so if the mass density is less than the critical, it'll expand forever. Greater than critical, it won't. It'll stop. The value can be of h0. You need to measure that accurately. And then you compare it. You compare the value of h0 to an average estimate of the density in the universe. You can estimate the density of the universe by counting the number of galaxies with an accurate mass of each, an estimate of each. And so you estimate the mass density. It's very hard to do it. Now, you'd have to have a very high mass to light ratio. And the evidence of this suggests the universe will expand forever. This was the conclusion that was reached 1990. 1990, we were tallying up the mass of the universe, and it was insufficient to reach the critical density. So the conclusion is the universe will expand forever. Okay, now these, we played with these already. I just want to do it again. Okay, remember that the universe is on a grid. These are galaxies on a grid. They take off, they expand, and meanwhile the curvature of the universe is curving down, and that is how it works. Alternatively, if you increase the mass density up to a high value and do it again, it doesn't get very far, and bang, goes back together. Now, that's not the universe we live in. We live in a more complicated universe. A universe that has a mass density and has a term called dark energy, which we'll discuss. We'll still got to discuss it. The dark mass needs to be higher in order to curve the universe a little bit. So up this. And the curvature now is negative. All right? It's always negative curvature. But that's not the way the data fits. The data was negative curvature and then positive curvature. So let me turn this on. Here it has a slight positive amount. If I turn it on high and turn it on, it curves negatively, but then it takes off when the other material takes over. This is called dark energy, and I have to describe to you what dark energy is. Okay, that is what we're going to do. That is necessary for you to understand. Okay. Okay, and the universe appears to be on this sort of trajectory. Negative curvature for a while, then positive curvature. That is the trajectory of the universe. This was done with a white dwarf supernovae. Type 1a supernova caused that to blow up. Okay. All right, so this was all observed, and it was amazing. When the universe didn't even fit the coasting model, we were amazingly surprised. Okay, that implied there's a dark energy in the universe. Okay, and the dark energy is a universe that doesn't collapse. It's not the critical universe. It's not coasting, but it is accelerating like this. This is a universe that has omega less than 1 and lambda. Einstein's equation. Einstein's fudge factor brought back to life. He threw the fudge factor out because he didn't feel it needed. He was using his fudge factor to make the universe static. But we have changed it around, and we can make it accelerate. Einstein would have been amazed to discover this, that this is possible, and another use of his constant. But lambda, this is the use of lambda. Greater than 0 makes it accelerate. Okay, how do you determine these things? Measure them with the standard candles. Okay, you can look at the deviations from the Euclidean law for the brightness. You count the number of galaxies in a volume of space. You just count how many there are. That turns out to be very sensitive to the curvature of the space. For example, if you double the distances, you expect 8 times as many galaxies because 8 times the volume. But if you measure less than 8, so less than 8 times, that means the universe has positive curvature. More than 8, negative curvature. Well, those are how you do it. And you look for signatures of a flat universe in a CMBR. Now, let's talk about the CMBR. Okay, now, this was extremely difficult to do. Let's skip this. All right, here is what we think the breakdown is. The dark energy term we think is 73%, or atoms, such as us, are 4% of the universe. That's all it is. Dark matter, that we said was around clusters and galaxies, is 23%. That is the breakdown. This is incredible. This, of course, the dark matter is still not discovered. Okay, we don't know what it is. All right, now, a universe with just atoms in it would be amazingly open, but it is not really open. Okay, what is this dark energy? We've got to answer that question. Now, there are alternatives to this model. This model was known as a steady state model, and it was advanced in the early 50s. People didn't know anything in the early 50s. They started speculating on the universe. This is based on a model of perfect cosmology, where they said steady state universe had no beginning. It just kept going. Had no beginning. Now, what's wrong with that model? If it had no beginning, then the universe just keeps collapsing. But we've got the Hubble constant, which says it had a beginning. And the universe is getting denser and denser. Well, if the universe is the same at all times, you better get rid of some of that matter. And so let's play it the other way. You start off in the universe and expand it, it gets diluter. And so the steady state model just said, oh, there's some way to make matter. They said, well, we'll make matter. They don't know if it can't be done, so they made matter, which is ridiculous. That doesn't work at all. They kept constantly make new matter, but that's silly. So that was completely crazy. And there were several arguments against it, particularly this microwave background radiation, and that's what I want to talk about next. What is that? This was discovered by accident by 2 gentlemen, Penzias and Wilson, who won a Nobel Prize for their accidental discovery. What did they see? These guys were working in 1964. They worked at Bell Labs with this big dish, and they were trying to use it to study. They actually used it to study the universe, see the sky around them, and there was a certain noise. No matter where they pointed this dish, they kept getting a noise, a noise like from all directions. And they didn't know what it was. What could that mean? Meanwhile, my advisor, Dave Wilkinson, and other people at Princeton were building an experiment to search for this remnant of the early universe, called the early remnant of the Big Bang. They thought that if the universe is really hot in the Big Bang, it should show signs of being hot. Anything that's hot has a black body radiation, we know. It should show a black body radiation, should be there. So they wanted to look for this black body radiation. Now, we're looking behind the sky, like this man. This is a medieval drawing. He's looking behind the sky to see what the mechanism of the sky really is. This is a cute picture. It's what you do when you study these really wacko things. All right, so the world, this was discovered in 1964, 40 years ago. 45 years ago. It was a completely different world. What was discovered in 1990-something was this spectrum. These points are the data, and the curve is a black body curve. It is such a perfect fit to a black body curve that the discoverer of it won the Nobel Prize too, as he should have. And it is exactly the same as a 3,000 degree black body, but it's scattered. What you say is the universe has expanded a factor of 1,000 since the last time this interacted with matter. This thing has redshifted by a factor of 1,000. And now its peak radiation is at 1 millimeter, right there. If you go back in time to 1,000, it was at the temperature of a red giant star. Okay, this is known as the microwave background radiation. This was discovered by accident in 1965, coming everywhere, and has a temperature that is now known, now measured very precisely, 2.7 degrees Kelvin, 2.73 degrees Kelvin. That is the temperature of the universe. Now, we're a little warmer than that here. This is Kelvin. You know, that's minus 273 Celsius. It's cold. So the universe's temperature is minus 200 degrees, 270 degrees Celsius. That's not our temperature, of course. That's the temperature of the universe. What do we mean by temperature of the universe? Okay, now, here is what has been discovered. This is totally, totally mind-blowing. You've got to understand what they're looking at. They looked, now, Penzias and Wilson could not see fluctuations. They looked here, and here, and here. Everywhere they looked, the microwave radiation was exactly the same temperature, to the best of their knowledge. But here, we've got a picture that takes away, it's like you tune the picture, you tune out all but a part in 10 to the fifth. You tune out all 9999 of the radiation is thrown away, and just look at the fluctuations on what's left. A part in 10 to the fifth, or 10 to the fourth, I'm sorry. 1 part in 10 to the fourth gives rise to these fluctuations. This is what This is what the universe looks like. Oh, God. Come on. This is the universe. This is the whole sky. And this was done with 7-degree resolution on a receiver of the cosmic background radiation that flew in the late 80s, 90s. Okay, they flew it again. They flew another experiment just completed a few years ago, known as WMAP, Wilkinson Microwave Anisotropy Probe, named after my advisor, Dave Wilkinson, who had died in the meantime, was very instrumental in the building of both of these experiments. This device has higher resolution, so we'll just look at this one. What you're seeing is a lot of crazy stuff. These are ripples, plus and minus ripples on the sky, really small ripples on the sky. These ripples made all the structure in the universe. These ripples made everything. It made galaxies. It made clusters of galaxies. It represents a small fluctuation in the universe. And the question is, how the hell did these ripples come to be? Why were they put into the universe at all? What was the horizon scale of the universe when this radiation was impressed? These particles, we're seeing the universe at a time when the universe is about 300,000 years old. That's what we're seeing. In that time, you're the horizon of somebody at the beginning, and if you measure the horizon at that time, the horizon was about this big. It was 1 degree was the horizon. And yet you see coherent structure over 300 degrees, 360 degrees. And the question is, how the hell did that get there? How were these fluctuations put in the universe when there was no time for anything to be put in the universe? We don't know how this was done. And this was a tremendous, tremendous mystery. Everybody argued about this, and nobody had any idea how to do this. This became the #1 mystery of the universe. Now, in addition, there's structure. These ripples have a structure like you have on a stereo receiver. If you play this frequency response, there's a big wave at just about a degree, and then smaller scales, there's other waves. This scale, this is the microwave radiation. The points are the data, and the curve is a model. This model seems to fit the data really well. Now, what do I mean by this model? This model is a lambda cold dark matter model, and it fits. What does that mean? Okay, this is a fundamental note in its harmonics. For example, if you're playing middle C, the middle flute and violin know what middle C is, but all the harmonics of them, you hear a flute and you know it's very different from a violin, but yet they have the same middle C. What they've got is the same fundamental wave. They've tuned their instruments so they have the same wave, but their harmonics are all different. Their harmonics tell you it's a flute or tell you it's a violin. That's what we mean by different sound to the instruments. You can tell what the instrument is by playing of this. And similarly, we don't draw this just draw it. It depends on all the universe's parameters. It depends on the dark energy, the dark matter, the baryons, lambda, H naught. All those parameters enter into drawing this curve. Those specify the harmonics. And with this, you conclude that the total omega is 1. The universe is closed. Now, the question is, what is the condition in the early universe? Okay, now, the universe started to emit to us. We see galaxies when the universe is just a few billion years old. Cosmic background radiation, we can't see beyond the cosmic background radiation. That's 380,000 years. And the cosmic background radiation represents the universe has a ground glass screen put up, like a shower door. A shower door, you can't see beyond a shower door because it's ground glass and all the light gets scattered in there. The universe is the same thing. The universe, at that point, everything gets, all the matter in the universe gets ionized. Instead of having hydrogen atoms, you have ions. You have electrons and protons. And the electrons scatter the photons. And you don't see beyond it. But you see the universe at that time. Now, what do I see? First of all, how do we know what conditions were like at the beginning of time? Here I'm drawing time, 10 to the minus 45 seconds, 10 to the 3, 10 to the minus whatever. How do we know this? How do we know anything about this? And the answer is, we know it very well because we can predict the temperature and density. The experimental evidence, we can know that the temperature of the universe scales as the expansion. As the universe expands, the temperature goes down. It's 2.73 degrees now. When went redshift 1, it was twice that. Redshift of 1,000, it was 1,000 times that, 2,700 degrees. Redshift of 1,000,000, it was 2.7 million degrees. Redshift of 1,000,000,000 gets very, very hot. It gets hotter than the center of stars. And we know that the centers of stars make all the elements. Everything is made in there. So in fact, we're not too surprised that elements can be cooked in the early universe because it was extremely hot. Very, very hot. You can run the expansion backwards and see the temperature going up. Here's the temperature from 100 degrees, 10 to the 4th, 10 to the 20th, 10 to the 32nd degrees. That's a ridiculous temperature. 10 to the 32nd degrees. Remember, the hottest we got in stars was down here, 10 to the 10th degrees. We're simulating the universe when it was about 10 to the minus, what is that, 10 to the minus 10 seconds. The universe was that hot. But we can simulate, we can study it earlier. Okay. And so we study all this stuff. We study the universe at different times. And next time we'll talk about what we can learn about them and what mysteries we have. And some of these mysteries are quite profound. So we have one class. I'll tell you what we do. We're going to talk about the universe next Tuesday. The week from, and that's the Thanksgiving week. The week after that, we have two classes. First class is going to talk about reconciling everything in the universe. That's going to be a very special lecture. You should come to that one. And the final lecture is going to be about life in the universe. And that'll be interesting. You should come to that too. All right? So everybody have a good Turkey Day. If I don't see you. How many people are taking off before Wednesday? A few. All right. The people who miss Wednesday's lecture can read about it on the notes, of course. Tuesday, yeah, Tuesday's lecture. You can read notes, and there's some sort of way you can follow this in B-space. Okay. I'll see you next week.